conductors, and we had seen there were two kinds of bands. One was the valence band and other one was the conduction band. And the gap between these two bands represented the energy band. So yes, we can classify conductors, insulators and semiconductors on the basis of band theory. So yes, regarding conductors, how are we able to distinguish from the rest too? Using
Conductors
band
have low
theory?
resistivity.
That was regarding resistivity. If you utilize band theory, then what difference does it make?
The conduction band and valence band overlap with each other.
Overlap each other. Either they overlap with each other, or there is energy gap between the completely filled valence band and what kind of conduction band is filled? In which way? Is
Sorry?
it fully filled?
No,
In
ma'am,
case
it's not fully. It's not filled.
it is partly filled.
Yes, ma'am.
In case of conductors, right? And in case of insulators,
The band energy gap is more than 3 electron volt, so there is
yes,
no conduction.
the gap in energy band gap is more than 3 electron volts. And is the conduction band completely filled?
No, ma'am, it is empty.
It is completely empty. Whereas valence band is
Completely filled with electrons.
completely filled with electrons. Regarding semiconductors,
The energy band gap is less than 3 electron volt.
yes, energy band gap is less than 3 electron volts. Now let us see, we have seen P type. In case of, we have seen semiconductors were extrinsic and intrinsic. And in case of extrinsic semiconductors, we had seen there were two types. One was the P-type semiconductor, other one was the N-type semiconductor. So in case of P-type semiconductor, what were the majority charge carriers?
P-type holes.
Yes, and in case of N-type,
Electrons.
electrons. Fine. Now see PN junction. What is meant by this PN junction? So this PN junction is basically a single crystal of, you can say, germanium or even silicon, which is doped in such a manner that half a portion of it becomes P-type and half a portion of it acts as N-type semiconductor. So here the term junction implies the boundary or region of transition between N-type and P-type semiconductors. If I represent it through this. So let's say this is the P-type portion and this is the N-type part. This is a single crystal. This is the, don't think that these are two crystals which are joined together. A P-type or N-type silicon crystal can be obtained by adding suitable acceptor or donor impurity into silicon. A P-N junction cannot be made just by placing a P-type semiconductor in close contact with N-type semiconductor. The two separate semiconductors cannot have a continuous contact at the atomic level. The junction will behave as a discontinuity for the flowing charge carriers. So both acceptor and donor impurities must be grown in a single crystal or silicon germanium. So PN junction is what? This is basically a single crystal which is doped with pentavalent impurity in half portion and trivalent impurity in another half portion. So if I want to make this half part as P type, should I take pentavalent impurity or trivalent?
Man, trivalent.
Trivalent. And if I want to make it the other half as N type, then
Pentavalent.
Pentavalent impurity. Fine, right. So I dope it with trivalent impurities. This half of the part will be of this crystal will be P type, and the other part that is doped with the pentavalent impurity will be the N type part. So if this is the P type part, it means it will be having more of holes. Holes will be in majority, while there will be electrons, but electrons will be the minority charge carriers. Whereas in case of N type, what are the majority charge carriers?
In N-type, ma'am?
Yes, in N type,
Electrons.
electrons. So this will be having more number of electrons within it, and the minority charge carriers, that are the p-type holes will be in very few amounts. So you can easily figure it out from this diagram also, that in case of p-type, holes are in majority and electrons are in minority, whereas in case of n-type, electrons are in majority while the holes are in minority. This is case of n-type. Now see, this is unbiased p-n junction. Now see, two important processes involved during the formation of this p-n junction. These two processes, one is the diffusion and the other one is the drift. First process is the diffusion, second process is the drift. These two processes occur in the formation of p-n junction. So when a p-n junction is formed, this way, p-n junction is formed. This boundary represents the junction which I'm talking about. So this single crystal has been formed as a p-n junction. For rest of you who have joined in late, p-type and n-type semiconductors we have discussed. Regarding p-n junction, this is a single crystal of germanium or silicon, any semiconductor, which if it is doped with pentavalent on one side, which it makes it as n-type, and when it is doped as trivalent on another side, it makes it as p-type semiconductor. And this junction represents this boundary between p and n-type. So as we were discussing, that two important processes involved during the formation of p-n junction. These are diffusion and drift. Now see, when a p-n junction is formed, the p side of the junction has higher concentration of holes, while the n side has higher concentration of electrons. Now from your even chemistry classes or your lower classes, what is meant by diffusion according to you? Simply, what is the meaning of diffusion? Yes.
Splitting.
No, not splitting basically. Diffusion is actually transfer of molecules through a gradient, mainly from higher gradient to lower gradient. So in case of this p-n junction, what happens? Due to the concentration gradient at this junction, holes are majority charge carriers in case of p, and these are minority charge carriers in case of n-type. So if holes are in majority in p-type, then where should the movement of holes occur? From p to n or n to p?
P to N.
P to n. So due to the concentration gradient at the junction, holes begin to diffuse from p side to n side. Again, if electrons are in minority in p type and electrons are in majority in n type, then electrons should diffuse from where? From p to n or n to p?
N to P.
N to p. So due to the concentration gradient, holes will begin to diffuse from p to n, and these electrons will begin to diffuse from n to p. Now see, as holes diffuse from p side to the n side, when the holes are moving, what will happen? If you have taken up a hole, deficiency of this hole will create a negative acceptor ion. Obviously, as the holes diffuse from p to n side, they leave behind negative acceptor ions, which set up a layer of negative charge or negative space region. See, when this diffusion will occur, these holes will be moving towards the concentration gradient. Then negative charges, negative ions will be set up. Why? Because of the deficiency of positive charges. So since holes are leaving, as the holes leave behind negative acceptor ions, which set up a layer of these negative charge or negative space charge region on the p side of the junction. Now tell me, as the electrons diffuse from n to p side, see, these electrons will be diffusing from N to P side. Then what kind of charge will they be leaving over here behind?
Positive.
Positive charges. So similarly, as the electrons diffuse from N to P side, they leave behind the positive donor ion. In this manner, they leave behind the positive donor ions, which set up a layer of positive charge or the positive space region on the N side of the junction. Now, as you can see, negative region has been created and a positive region has been created due to diffusion of holes and electrons because of the respective concentration gradient. Now, this sets up an electric field near the junction from N to P side because of these positive charges and because of these negative charges. This creates an electric field near the junction from N to P side. So any hole near the junction is pushed towards the N side, and similarly, any conduction electron near the junction is pushed by the electric field towards the P side, whatever phenomena is occurring. So what will happen? Consequently, no charge carriers are left in the small region near the junction. So this small region in the vicinity of the junction, which is depleted of free charge carriers, has only immobile ions. And this region is called the depleting region. Depletion region. This region is called the depletion region. So again, repeating. So this electric field which has been set up because of negative charges in the negative direction and positive charges in the N type because of diffusion of electrons and holes. So this creates electric field, and this electric field near the junction pushes electron holes towards the N side and similarly pushes the electron to the P side. And then no charges are left in this small region. This small region in the vicinity of junction, which is depleted of these free charges and has only immobile ions. This region is called the depletion region, or you can say depletion layer. Now see the distribution of charge near this junction. This accumulation of the negative charges in P region and positive charges in the N region. This sets up a potential difference across the junction. So you're already aware of the terms electric field potential, and the creation of these ions, negative and positive ions, will be setting up the electric field and the potential. So the accumulation of negative charges in the P region and positive charges in the N region sets up a potential difference across this junction. So a potential difference is also set up across this region. So this acts as a barrier, and this potential, this is called as the barrier potential. So accumulation of negative charges in P side and positive charges in N side sets up a potential difference across the junction, which is known as the barrier potential. Now see, this barrier potential, this opposes the further diffusion of electrons and holes across the junction. So only those electrons and holes holes which have energy, at least EV in the sense electronic charge multiplied by this barrier potential, EV, these are only able to cross this barrier, and some diffusion takes place. So this diffusion of majority charge carriers across the junction gives rise to an electric current from P to N side. Electric current will also be now set up. All the phenomena that we have studied in current electricity and electrostatics will be used over here. So this diffusion of majority charge carriers across the junction gives rise to an electric current from P to N side, and this is called as the diffusion current. So is this clear how the barrier potential is set up? What is meant by PN junction? What is the depletion region? So this was regarding the phenomena diffusion. See, one more phenomena is there. Yes.
Ma'am, could you explain the barrier potential again?
Sorry, what?
Barrier potential. Could you explain it again?
Yes. See, firstly, diffusion, you have to understand what is diffusion. Two processes are occurring, diffusion and drift. These two processes are occurring. So diffusion is flow of the majority charge carriers across the junction. Means flow of holes from P to N and electrons from N to P, which I have already written over here. So this is the basic phenomena of diffusion. Now see, in case of diffusion, what happens? When holes are moved towards the N side, this creates negative charges. Means you can say negative ions are there. And when electrons diffuse from N to P side, this creates positive acceptor ions. So negative layer is set up and positive layer is set up. So distribution of charge near this junction, this is in this manner. In place of P type near the crystal, negative charge layer is set up, and in case of N type, this positive layer is set up. So this accumulation of these negative charges in the P type and positive charges in this N type part of the semiconductor, this creates a potential difference. Positive and negative charges have potential differences between them. So these layers will also be having the potential differences. So this potential difference acts as a barrier to stop the further diffusion. That's why this potential difference is named differently, that we call as the barrier potential. So this acts as a barrier, and this is called the barrier potential. And this is called as barrier because it opposes the further diffusion of electrons and holes. So only those electrons or holes which have energy more than this, means E multiplied by VB. You write the kinetic energy as EV. From your modern physics, you have already studied kinetic energy is E multiplied by V. So if electronic charge is multiplied by the barrier potential, then this gives the energy. And if any hole or electron is able or has at least this much energy, then only it will be able to perform the further diffusion. Since this is stopping most of the diffusion process, that's why we call this potential difference as the barrier potential. So this difference is called as the barrier potential difference, which is set up. So this potential difference sets up electric field across the junction, which further opposes the movement of majority charge carriers. This is known as barrier potential, and this region through which barrier potential has been created, this is known as the depletion region. Is this clear now?
Yes, ma'am.
So this barrier potential will set up electric field in direction from N to P side. Now see, in the depletion region means this part. In this depletion region, electron hole pairs are continuously produced due to thermal or electric field conditions. Now see, because electron and this negative charge and positive charge means electron and a hole, these pairs have been created. So what happens? The electric field immediately pushes the electron towards the N side, back to the N side, and the electric field pushes back these positive charges into the P side in their respective from which they began. So what happens? This electric field, when it pushes electrons towards the N side and holes towards the P side, a current is set up. So this current set up by this barrier field, because of that electric field, the current that is set up from N to P side, this is known as the drift current, that we call as drift. So due to electric field, minority charge carriers have crossed the junction known as drift. So what kind of charge carriers did travel through diffusion? Only the majority charge carriers traveled through diffusion, whereas drift helps in movement of minority charge carriers. Why? Because of drift current, because of this phenomena of drift, that is the electric field that has been set up, it helps to regain these positive charges back to the P side, and electronic means the negative charges back to the N side. So diffusion helps in movement of majority charge carriers, while drift helps in movement of negative charge, minority charge carriers. So are these concepts clear? See, P and see these definitions. Diffusion is the flow of majority charge carriers across the junction, and flow of holes from P to N and electrons from N to P. Then barrier potential, then drift. Now see, if I tell you movement of holes, if I summarize it, movement of holes from P to N. This is because of diffusion. Because holes were the majority charge carriers in P and electrons were the majority charge carriers in case of N. While the movement of electrons from N to P, this is because of diffusion. Because electrons were also the majority charge carriers in case of P. So this phenomena is occurring due to the process of diffusion. Now see, when electrons move from P to N, now this is occurring due to the phenomena of drift. Drift means that electric field that has been set up. And when holes move from N to P, this is because of the drift. So these two processes are occurring because of the phenomena of drift, and this process is occurring because of the phenomena of diffusion. So diffusion and drift, are these two concepts clear? And PN, formation of PN junction. Yes, just note it down, this part. Yes, done.
No, ma'am.
Yes, completed.
Yes, ma'am.
Yes, ma'am.
See, one more thing. In case of equilibrium, this diffusion process, this becomes equal to the drift process. So what kind of movement will take place if diffusion and drift are equal?
Equilibrium.
Equilibrium, this means no net movement. So no net movement of charge carriers. No net movement of charge carriers. And also regarding the depletion region, it does not have any charge carrier. Means depletion region, it will have neither electrons nor holes. Now see, regarding the PN junction diode. PN junction diode, this is the same. It consists of PN junction with metallic contacts. Now see, if we represent it through, this is the crystal that we use. Let's say this is the P side, this is the N side, this is comprising more of the holes, less of electrons. This is the N side comprising more of electrons and less of holes. Now see, this will create a barrier potential because of the accumulation of negative charges in the P side and positive charges in the N side. And so barrier potential will be created. Now see, if we put metallic contacts, these are the metallic contacts. Now see, if we put metallic contacts in case of PN junction diode, this forms a diode. Now how do we represent it? This P part is represented through a triangle in this manner, and this end region is represented through a straight line like this. See, in this manner. This is the P type, this is the N type, and the metallic contacts means the wires. These are represented through this. So this is the basic representation of P and N type. Now see, P and N type have two types of biasing. Means one is when it is the way we have working of a junction diode when it is forward biased, and other one is when we have the junction in reverse bias. So see, regarding forward biasing, let's say this is the P part, this is the N part. In between, negative ions will be in this part and positive ions will be in N part. This will be having its barrier potential, that is VB. Now see, how do we differentiate forward and reverse biasing? If the positive terminal of the battery is connected to the P side, means this part of the battery, this positive part of the battery, this is connected to the P side, and the N side, N part of the battery is connected to the negative side. This setup, this is known as forward biasing. In case of reverse biasing, we'll be having P part again, N part again. This will be comprising the depletion region. this will be comprising of the positive acceptors. So, and here a potential barrier will be created similarly. Now see, regarding reverse biasing, if this positive terminal of the battery is connected to the N side, means this N part of the battery, now this part has the positive side and the P part is connected to the negative side. This is the reverse biasing. This is the major difference between forward and reverse biasing. In case of forward biasing, the negative part, the positive terminal of the battery is connected to the P side and the negative terminal to the N side, then the PN junction is said to be forward biased. So see, in case of this setup, if this positive charge is over here and negative charges over this side, negative terminal of the battery. Now see what kind of flow will occur. This positive part of the battery, this negative part will be attracting the positive part, and this negative part will be get attracted by this positive terminal of the battery, because positive is over here and negative is over here, and positive is over here and negative is over here. Now see what will happen. Flow of majority charge carriers will occur, means from the hole, these holes will be pushed up because of repulsion between positive. Similarly, electrons are over here. Electrons will be pushed up because of this repulsion between negative. So electrons will be moved. So what kind of charges are moving? Majority charge carriers or minority? Majority. So flow of majority charge carriers across the junction occurs. This happens. So as a result, what happens? Since the respective charges are able to move, what is recurring or what is getting disturbed? Barrier potential is getting disturbed. So that's why whatever is the barrier potential, let's say VB was the barrier potential. Now it will be less than VB. So let's say V is the potential of this battery through which is connected. Now the barrier potential, it will decrease to what? VB minus V. Barrier potential gets decreased in case of forward biasing. Now see what will happen as the positive charge carriers will move towards N side. So more of negative acceptor ions will be created on this side. As the electrons will move back to the P side, more of positive part will be created on this N side. So tell me, depletion layers width is increasing or decreasing? Yes, say.
Increasing.
See, it will keep on increasing. As more positive part will go, more electronic part will come here. It will create more of vacancy and deficiency over this side. So that's why width of depletion layer or width of depletion region, this also decreases along with the barrier potential. And one more thing, if we talk about resistance, so resistance of the depletion region, this will also decrease.
Ma'am?
Yes, sir?
Ma'am, width of depletion region will decrease or increase?
It will decrease in case of forward biasing. See, majority charge carriers are moving. If I say holes are the majority charge carriers in case of P type. All right. Now see this positive charge, this. See now this positive charge has moved and it has reached this N type, N part. So majority charge carriers are moving, means holes are moving from P to N in case of P type. So when a hole moves from P to N, what gets created? Negative ion gets created because of the vacancy of the hole. Similarly, when electrons will be moving, as electrons are the majority charge carriers in case of N. So when electrons will move from N to P, positive charge carriers will be created because of the vacancy of electron. So because more of the majority charge carriers are getting interchanged, this is creating more of negative part and more of positive part. So this, by this, the depletion region will widen itself. Fine.
Yes, ma'am.
Okay, now if you even represent it through the diagram, which through the representation of it will be in this manner. This is the P part, this is the N part. P part is connected to the positive terminal of the battery, while the N part is connected to the negative terminal of the battery. This is the P part, this is the N part. In this manner, current will flow. And since you can even represent it through graph also, if this is the potential of P part, this is the potential of N part, this difference between it will represent the barrier potential. Now see, just reverse occurs in case of reverse biasing. Firstly is the setup. The setup means the positive part of the terminal of the battery is connected to the N type and the negative part is connected to the P type. So see, in case of this, holes are the majority charge carriers in P, while electrons are the majority charge carriers in case of N. Now see, what will happen when we have set up this apparatus and when the current is drawn in? Electrons and holes are there in their respective places initially before the setup or the current has begun. Now electrons are over here in minority and negative part is here. So now the negative part will not be able to push positive part. Instead, it will attract the positive part. It will repel the negative part, means the electrons. So now the electrons will move towards the inside. Now in case of inside, look at this part now. This is the positive terminal part of the battery. Now see, it will be attracting all the holes which are in majority, and this positive terminal part of the battery will be attracting the electrons while it will be repelling or pushing back the holes. So the holes will go. So now see, electrons are moving from P to N and holes are moving from N to P. So what kind of charges are moving?
Minority.
Minority, right? So here, minority charge carriers are across the junction. And here the barrier potential, since the work of barrier potential was to stop diffusion. Now diffusion is getting stopped. This was the work of barrier potential. So barrier potential will increase or decrease?
Increase.
Increase. Barrier potential, it will increase. So if I say V is the potential of this battery, now barrier potential total, it will get added with this potential of this battery. Now see, since electrons are moving back, so means this negative part is also getting reduced, and since holes are moving back to P type, this positive part is also getting reduced. So width of depletion region, what should happen near the width of depletion region?
Decrease.
Increase.
Increase. Width of the depletion region, it will now increase. It got increased in case of this forward biasing. It got decreased in case of forward biasing. Now it will increase. And resistance also increases. Resistance will be more. So even if you represent this PN junction, it will be in this manner. This is P, this is N. This is connected to the negative part, while this is connected to the positive part. All right, just note it down. this was which I was explaining regarding the reverse and also. So when you are writing it for the forward, just narrow down the width of depletion region. Since this is getting increased in case of reverse, so when you are drawing the reverse biasing part, just draw the negative charges over here. Now this will represent the widen width and this will represent the decreased width. Now since electrons and holes are diffusing into this layer, so this will decrease the width. So by this it will represent it.
Ma'am,
Yes.
could you explain the width of the depletion layer, how it increases or decreases?
Okay, let's see. See, in case of forward biasing, majority charge, actually I've explained both of them together in this one, that side, might be confusing. See, first let us see only forward biasing. Now see, in case of forward biasing, what are phenomena, what all the phenomena are occurring? The effective barrier potential, this decreases. So energy barrier across the junction will decrease. Now see the majority charge carriers, that is holes from the p side and electrons from the n side. These begin to flow towards the junction. So positive part is flowing towards this junction. Electronic means negative part is flowing towards the junction. So if I tell you positive part is there, negative part is there. Can you tell me, is this positively charged or negatively charged? This part.
Ma'am, it's neutral.
It's neutral, exactly, because of the recombination. Both of these will recombine. This part is neutral. So now see, if there were, let's say this was the negative charge, and I've, because of this flow of the majority charge carriers, a positive charge has come at this way. So this part, or let's say this was the initial layer. This was the thickened widened layer. Now see, since positive charges are coming across, what will happen? Ultimately, this part, this will get recombined, this will be recombined, this part will be neutral. So here it will get decreased. Similarly, electrons will come and it will neutralize this positive part. Electrons will neutralize this part and electrons will again neutralize this part. So is the width of the layer decreasing or increasing?
Decreasing.
Decreasing. It will decrease. So that's why in case of forward biasing, we say the width of the depletion region decreases. Now see, in case of reverse biasing, what phenomena are occurring? Firstly, as a result of this application of the positive part of the positive terminal to the inside and negative terminal to the p side, barrier potential increases and hence the energy barrier across the junction increases. Now see, majority charge carriers now move away from the junction. If you are not able to remember it through this minority movement of minority charge carriers, you can look at this way, that this is flow of majority charge carriers away from the junction. If I say electrons are moving from P to N side, it means holes are moving from, means away from the junction. Holes are moving from positive to negative side. You can even reverse it that way. So majority charge carriers are now moving away from the junction. Why? Because the minority charge carriers are moving towards the junction. So what will happen as a result? This will increase the width of the depletion region. See, electron will be moving towards this side. So this will be creating more of the vacancy. As the positive part means the minority charge carrier, that is holes, these holes will be moving from this N type to P type. So this will creating more of vacancy. So ultimately what will happen? Negative charges or you can say negative charges means the minority charge carriers from N side. These will get accumulated across the junction and the minority carriers, that is electrons from the P side, these will get accumulated from towards this junction. So as these charges are getting accumulated, what will happen? The width will increase or decrease?
Increase.
Increase. In case of forward biasing, what happened? There was recombination of electrons and positive part pairs were occurring, since both of these were getting towards the junction. In case of reverse biasing, these are moving away from the junction. So as it will be just the reciprocal of this phenomena. Here, positive part was coming towards the junction and it was neutralizing it. Now electrons will be coming. So electron, if I say electron and electron pair is there. So is it positively charged or negatively charged?
Negatively charged.
Negatively charged. So that is how happening in case of reverse bias. Electron is coming towards the junction. So electron will not neutralize it. This will create more of negative part. So similarly, positive part is coming towards the junction. So it will not create a negative part. It will not neutralize it. Positive will be what? It will be positively charged. So because of this accumulation of charges across this junction, this is widening the width of the depletion region. Faisal, is it clear now?
Yes, ma'am.
No. So yes, written all of you?
Yes, ma'am.
Okay, now let us see if you are provided with PN junction. So you should be able to identify whether it is positively charged or negatively charged. So let's say this is a PN junction diode. This is the P part, this is the N part. Here, let's say this is 10 volts, this is plus 3 volts. Fine. Now see, how will you identify whether it is forward or reverse bias? By looking at these kind of diagrams, because you are not able to identify whether it is negative terminal or positive terminal. So what you can do, when the P part or P type is connected to that terminal which has higher voltage, then we say this is forward bias. Had it been opposite, means 3 volt had been over this side and 10 volt had been over this side, then it would have been reverse bias. So if you are provided with this kind of apparatus, just look at the voltages. If positive part, or I mean the higher part is connected to P type and the lesser of the part is connected to N type, means this is forward bias. So I'm giving you more of these questions. Just write down, draw it right now only, and then we'll discuss whether it is forward or reverse bias. You just have to look which one is greater. So see, we have discussed the first part. Let's see the second part. So yes, write down in the chat box right now whether it's reverse or forward bias. This one, second one. Only Abdullah and Faisal have answered. Yes, Fatima, Noor, Sania. Abdullah, are you saying forward or reverse? There are two answers given by you.
Ma'am, for all the three, till fourth question I've answered.
Okay. Till fourth you have answered. So yes, the first part, it will be this. Regarding the second part, this will be C. +3 is connected to P side and -3 volts is connected to N side. Means higher part is connected to P and lower part is connected to N. So this is definitely forward bias. Regarding the third part, yes. Yes, Noor, Sania, and Fatima. Only Faisal and Abdullah are answering. Yes, it will be reverse because 10 volt is greater and 5 volt is lesser, and opposite have been connected. So this will be reversed bias. Fourth one will, yes, it will also be reverse bias. Because see, -3 volts, this is greater than -10 volts. So this will be reversed. Now see, fifth part. Yes, answer the fifth part now.
Ma'am, what is that arrow mark?
These represent earthing symbol. So if
Ma'am,
it earthing.
Earthing means potentially zero, right?
Exactly. Earthing means potential is 0. So it means potential is 0 over this side and it is 5 volts over P side. So it will be forward. Yes, right, forward. It will be forward bias because higher is 5 volt is obviously greater than 0. Sixth part, it will be reversed. Yes, because this is 0 and this is minus 1. This will be reversed. So all of those who have not done this, just write it down. Then we'll do one more concept, which will be utilized in your current electricity as well. Yes, done.
Yes, ma'am.
Now see one more concept that is connected and related through your to your current electricity chapter. See, in case of forward biasing, in case of forward bias, when the circuit is forward biased, and you have this diode, this is the P part and this is the N part. So here resistance is small. As I've told you, the effective resistance across the PN junction this decreases. So this is so small that you can approximately equate it to 0. So if you remember, you have done in your current electricity, when resistance is very, very, very small, then we say what kind of circuit is this?
Short circuit.
Short circuit, exactly. So this will be a short circuit, means this can act as a straight wire. In case of reverse bias, just opposite to it. In case of reversed bias, the resistance will be very large, means approximately equal to infinity. Then what kind of circuit this will be? If there's so much of resistance. Yes, if this is short, then this will be what? Yes, Abdullah.
Ma'am, I forgot the name of this circuit.
Faisal, do you want to try?
No, no.
See, when resistance is so large, means current is almost
Large
negligible.
circuit,
Open circuit.
open circuit.
Did you recall, Abdullah? This was the open circuit which you have done.
Yes, ma'am.
This is the short circuit and this is the open circuit. Because there won't be any current because the resistance is so much. So see, if you get even questions based on this, if I give you any random question based on this, like say this is a diode and this is connected to 10 ohm resistor, and I have another diode with me, and this is also connected, let's say 20 ohm to some 20 ohm resistor, and these further are connected to, let's say 10 volt with 10 ohm resistor. This is the question I have given to you, and if I ask you to calculate the equivalent resistance, what is the effective resistance? Now see, if you just look at this first diode, you will be able to deduce it. So is it forward biased or reversed biased? Just forget everything and look at this PN diode.
Forward,
Why forward?
because positive terminal of the cell is connected to P.
Right. This is connected to the positive part, and this N type is connected to the negative part. So this becomes This will be forward bias. Look at this one.
Negative. Reverse.
Reverse bias, because N, this is P. N is connected to the positive part, P is connected to the negative part. Now see, as I've told you, if it is forward biased, we can replace it through a single wire. So if you are given this circuit, you know how to solve it. How? See, you can replace this by a single wire. This is 10 ohm. And this is short circuit, means no current will be flowing through it. There won't be any current going through it. And again, you have the battery with you. This is 10, this was, yes, 10 ohm, this was 10 volt. Now look at this. Is this wire even functioning? Because no current is flowing, so this is of no use to us. This is a simple 10 ohm circuit connected to another 10 ohm resistance with a battery of 10 volts. So are these in parallel with this wire along, one wire in the middle? Are these connected in parallel or series?
Series.
Series. So R equivalent will be
20 ohm.
20.
20. 10
Right.
plus 10.
Yes, right. So if you have to find out the current even, this is not part of the question, but if they ask you what is the current, then for the current also you can calculate. You know the voltage and you know the resistance. This will be 10 volts. 10 volt is there, and this will be 10, 20.
20.
So this will be 1 by, so this is not 20, just 10. So this was 20. 20 how? 10 plus 10 ohm. Voltage is 10, equivalent is 20. This will be 0.5 ampere. Clear? So will you be able to deal with these circuits with positive and negative part? Just note down these two also, how to deal with circuits. Then we'll see characteristics of PN junction diode, and that will end your diode part. Now see characteristics of PN junction. If you remember VI characteristics. Characteristics basically means graphical representation. So VI characteristics of a PN junction diode, it will be a graph showing the variation of current flowing through a PN junction with the voltage applied across. So both when it is forward and when it is reversed bias. This is called a voltage current or VI characteristics of PN junction. Majorly VI, whenever you see characteristics of VI graph, VI part or for PN junction also, it means this is representing the graph. It's a graphical representation showing the variation of current. Now see, one for forward bias, if I have it, see, firstly the setup before telling you the graph. This is the P, this is the N part. Now see, a voltage has been connected in order to measure this. This is the forward bias characteristic. So this is experimental arrangement for studying the characteristic curve of PN junction when it is forward bias. So a battery is connected across the PN junction diode through a potentiometer or rheostat. So rheostat is represented through this symbol. And this is the battery that has been connected, positive part and the negative part. Now, one thing that you have to remember in case of forward biasing, current is measured in milliampere. So the ammeter will be measuring in milliamperes. Now see, if we draw the characteristic graph of it, see what will happen. The milliammeter measures the current through the diode. So for different values of voltages, the different current is noted. So a graph, when it is plotted between the voltage and the current, means let's say current is over here measured in milliamperes and the voltage is measured in volt. This is the voltage measured in volt. So experiments show that initially it will increase. Initially, the current increases very slowly, almost negligibly in this manner, as you can see, till the voltage across the diode crosses a certain value. You can even call it the threshold voltage or cut-off voltage, cut-in voltage. After this voltage has been crossed, let's say this is the knee, or this is also called the knee voltage. So let's say this is the knee voltage. So till here, this increases very slowly current. Now see, after the cut-in voltage or this knee voltage, the diode current increases rapidly. Or you can even say it increases exponentially in this manner. So here the majority charge carriers face negligible resistance at the junction. So resistance across the junction is quite low. So even if you have to calculate the slope, so this will represent you the change in current. This part will represent the change in voltage. So whenever you have to calculate the resistance, taken in this manner. This part will give you the current, whatever is the reading, and this will give you the voltage, whatever is the reading. So R will be delta V divided by delta I. This is from your Ohm's law. This will be regarding forward biasing. Now, if this was the setup for forward biasing, if I draw the similar setup for reverse biasing, let's say this in case of reverse biasing, this is the P type, this is the N type. Again, voltage has been connected, voltmeter has been connected, potentiometer or this rheostat, this is connected, and a battery of higher power, higher voltage, this is connected. Now see, in case of reverse bias, it will measure, the ammeter will measure the current in microamperes. How did it measure in case of forward bias?
Milliampere.
Milliameter.
Milliampere. Yes, milliampere. In case of reverse bias, it will measure in case of microampere because the current will be lesser. Now see, if you see the graph. Graph means if you look at the characteristic. Characteristic means the reverse characteristic for it. So see, regarding the reverse bias, experimental arrangement is this only. This is the experimental setup. Now here microammeter is used to measure the small currents through the reverse bias. Now see, when the diode is reversed bias, the reverse bias voltage produces very small current. So similarly, this will be producing very small current. Let's say about few microamperes, this will be producing current. Now see, after again it crosses the breakdown voltage. Once it crosses the breakdown voltage, it will reach sufficiently high value. So the reverse current suddenly increases to a very large value in this manner. So this is representing the voltage and this is representing the current in microampere. Now see, if I give you a graph which will be comprising of both of these. Let's say this is the graph if I give it to you. So, this is for the forward part and let's say this is for the reverse part. This is the graph that is given to me. And let me tell you the readings also. There are three parts which have been marked. This is, let's say 10, this is 15, this is 20. So in case of forward biasing, what will be the unit, micro or milli?
Milli.
Milliamperes, yes. And let's say this represents 1. So this will be current in micro or milli?
Micro.
Microampere, yes, correct. So let's say this voltage is minus 10 and this is 0.5. This is unknown, not given to you. This is 1 and this is the voltage given in volt. Now, if I ask you, this is the graph given to you. Now see, if I ask you to calculate the resistance, if I say calculate resistance at first part, if I say I at 10 milliampere, let's say second part I at 15 milliampere, and the third part current at 1 microampere. This is the question given to you. Now see, for current at 10 milliampere, 10 milliampere means this part. So what is the corresponding voltage to this 10 milliampere?
0.5.
0.5. And what is the relation between resistance, voltage and current?
V is equal to IR.
V is equal to IR. So R will be equal to V by I. So since V is 0.5 and I is given as 10 milliamperes, mean 10 to the power minus 3. So this will be 50 ohms. This will be the resistance at current for 10 milliampere. Now see, regarding the second part, are you able to see any value of voltage?
No.
So you have to take the average whenever this is given. Now see, how will you take the average? Firstly, I1, you will take the initial value ahead of it and behind of it. So I1 is 10 milliamperes, I2 is 20 milliamperes. So if you take out the difference between two, delta I, I2 minus I1, this will be 20 minus 10, that is 10 milliamperes. Regarding voltage, V1 corresponding to this 10 milliampere is 0.5 volt and V2 corresponding to 20 milliamperes, which we know that is 1 volt. This is given. So again, voltage difference, this will be 1 minus 0.5, that is 0.5 volt. So see, what will be the resistance? The resistance will be delta V divided by delta I. So this will be 0.5 divided by 10 into 10 to the power minus 3. This will be given 50 ohms. This will be the resistance. Now regarding the third part, that is current at 1 microampere. So now look at it. Look at the graph. What is the current at 1? What is the value of voltage at 1 microampere?
1 volt.
Minus 10.
1 volt is this current.
Minus 10.
Minus 10. So see, minus 10 is actually representing because it is given in this direction. So you can take just the magnitude to calculate the resistance, because see, resistance cannot be negative. So that's why we just take the magnitude. So this will be 10 divided by 1 micro means 10 to the power minus 6. This will be 10 to the power 7 ohms. Is this part clear?
Yes, ma'am.
So just write down the characteristics of both these. Then very small topics are left. Now see, rectifiers. The process of converting alternating current into direct current is called rectification, and the device used for this process is called the rectifier. So see, rectifier basically it converts AC into DC. Like the best example of rectifier is your mobile phone charger. Now see, these devices are rectifiers. So see, when a PN junction diode, this is forward bias. It offers less resistance and current flows through it. But when it is reverse bias, it offers high resistance and almost no current flows through it. So this unidirectional property of diode enables it to be used as a rectifier. So when AC signal is fed to a diode, the diode is forward biased during positive half of cycle and current flows through it. And during the negative half of cycle, the diode is reverse bias and it does not conduct. And see, rectifiers are also of two types. One we have as the half wave rectifiers, and the other we have as the full wave rectifiers. Now see, let us briefly discuss what are half wave rectifiers and what are full wave rectifiers. So first let us see so the arrangement consists of a step down transformer. Let's say this is the step down transformer. This is the power supply. This is the power supply. And this is a step down transformer. So half wave rectifier consists of a transformer. Junction diode is also there. So junction. Consists of a junction diode. This is a load resistance that is connected for the output. This is the load resistance connected for the output, and this is current for the input. Now see, when AC is supplied to the primary, the secondary of the transformer supplies desired alternating voltage. So during the positive half of cycle of AC, this end is positive. So if this end is positive, then what will happen? Will the current be there or not? Will the current pass or not?
Yes, ma'am.
It will. See, positive is connected to the positive. So let's say it will conduct. So let's say this will be, and see, positive part will be over here also. So negative part will be here. I have taken the positive here. So see, positive is there, negative is there. Since positive and negative are towards this, see what are these positive and negative? When AC is supplied to primary, secondary of transformer supplies desired alternating voltage. So during the positive half of cycle, this end is positive and this end is negative. So since this diode is PN junction diode, this will be forward biased. So it will conduct. This is voltage, this is time. Now see, now what will happen? Now during the second half of the cycle, what will happen? This part will be negative, this will be positive. So now it will be reversed. So will it conduct any current or not?
No.
So this won't be conducting any current. Then again, had it been AC, for AC this would have been conducting. It would be negative and this would be positive. This is case of AC, the frequency of AC. But in case of DC, It will be only positive. It will be only positive over this side. So this is the frequency of DC. Now see, if you talk about the full wave rectifiers, if we talk about the full wave rectifiers, see what happens there. Power supply is there. The step down transformer is there. This apparatus is same. In case of this apparatus, this diode is over here and we have two diodes. This is connected. These are two diodes. And then we have a center tap, which is a res. This is called a center tap. This is the arrangement for the full wave. So now what will happen if we have a positive end and a negative end? So let's say this is the graph. And now say this is the negative end and this is the positive end. So this will be reversed biased. But this second diode, this is the first diode, this is the second diode. This will conduct. So we'll again get an output. Now see, when it will get reversed, this will be positive, this will be negative. This won't be able to conduct, but this part D1 will be able to conduct. So what? We will be able to get another curve, another output, this unidirectional output. Now when again it will be negative, this will be positive. So this will be able to conduct. So are we getting continuous graphs or interrupted?
Continue.
Continuous. So this is the frequency for DC, and had it been AC, there would have been any change. This is positive, negative. And what are these graphs and frequency of AC, DC? You have already studied in when you must be studying AC and alternating current lesson. So can you tell me any relation between the frequencies of half wave and full wave? Are they same?
No, ma'am.
So one is double of the another. See, this was half wave rectification. In case of full wave rectification, when this process of full wave rectification occurred, that arrangement was known as the full wave. So it had both the cycles of input. So for full wave, it will be double of it. Are you able to see this? See this, when it is covering this only, it is covering here. Now when there is no graph, it has already covered 2. So frequency over this is 2. Frequency over here, it is 1. So this is doubled of it. Just write down rectifiers as well. Then we have very few special purpose PN junction diode. That will end your lesson. special purpose PN junction diode. So see there in this you have Zener diode, you have photodiodes, LEDs which you are aware of, and solar cell. Now see, Zener diode, which was a very broad topic, this has been deleted from your syllabus. So now you only have to remember the graphs and very few details of photodiodes, LED and solar cell. So if we begin with photodiodes. So basically photodiode is a PN junction that is fabricated from a photosensitive semiconductor and is provided with a transparent window so as to allow light to flow into the junction. So in this manner, this is the P part, this is the N part. It is connected, this is connected to the negative part. So tell me, is it forward biased or reverse biased?
Reverse.
Reverse bias, yes. So this is covered by the major points which you have to remember include that it is covered by a transparent photosensitive semiconductor. Transparent window is there, so that light can fall on it. Like if this is your semiconductor, this is covered by this transparent window, then light will be able to come. So, and one more thing that is important that you have to remember is that it is reverse bias, and major function of it is that it is used to measure the intensity of light, used to measure the intensity of light. So this is a photodiode, and one thing that you have to remember is regarding its graph. So since it's a reversed bias, it will be measuring the current in microampere or milliampere.
Microampere.
Microampere.
Yes, microampere. So see, if you draw the various currents for different voltages, you will get it in this form. So this is the dark current you will get. This will be of the most intensity. This will be the for the dark current. Then the intensity you have, it will keep on changing. And by this you will be having the various graphs. This will be I1, this will be I2. See, these I1, I2, these are not the current. These are representing the intensities. I1, I2, this is how the graph of the photodiodes look like. One more thing, that energy is greater than the energy gap. So that's why, because of this property of photodiodes, it is able to allow current to pass, because when a photodiode is illuminated with light of photons of energy, h nu is greater than Eg. This energy is greater than means h nu is greater than the energy gap. This is the condition. So increasing intensities are occurring, I1, I2, I3 and so on, these are increasing. So value of reverse saturation current increases with the increase in intensity of incident light. So a measurement of change in reverse saturation current occurs on illumination, which can give various values of light intensity. So if I1, I2, these are the current, I2 will be greater than I1 and so on, the order will go. I2, I3, I4, how many you have? So I4 will be the greatest in this manner. So this was regarding the photodiode. Then a device you have called as the LED. What is the full form of LED?
Light emitting diode.
Light emitting diode. This is light emitting diode. So see, it is a heavily doped diode, PN junction, which spontaneously converts the biasing electrical energy into optical energy, like the infrared and the visible lights. So see, regarding its reversing, it is forward biased. So it's a heavily doped forward biased PN junction. If this is your LED, it will be emitting light. So what is the difference from photodiode? In case of photodiode was the receptor of light. Now this is emitting out light. So this is material, the material that is majorly used in these formation of LEDs. Materials used in LEDs. These include arsenic, gallium, phosphorus. These are for the red LEDs. These materials. And for the infrared LEDs, you use gallium arsenide. So these are the major points that you have to remember in case of LED. And one more thing regarding its graph, since it's a forward biased graph, so current will be measured in
milliampere.
Microampere, milliampere.
milliampere. Yes, right. It will be measured in milliampere. So this is, and here we'll be having a knee voltage as what we have already discussed in forward biasing, reverse biasing. Once you are aware of the biasing term, which bias is getting included, then you already should know that rest of the properties will be matching. Third one or the last one is the solar cell. Now solar cell, this converts the solar energy, means the energy of the sun, the solar energy into electrical energy. This converts solar energy into electric energy. So solar cell's work is to first to receive the cell. So it is a junction diode which converts solar energy into electricity, and it is based on photovoltaic effect. Photovoltaic effect means the generation of voltage due to bombardment of light photons. So it has a top surface. This is basic construction of it also includes material silicon or gallium arsenide. So thin layer is there, wafer kind of structure is there. Thin structure is there, and it receives light, and then it converts it into electrical energy. So basically like in this form. In wafers form it is there, N type and P type are there. And then metallic finger electrodes are there placed on the top, and these receive light. So this is the basic, or you can represent it in this way also. Like if this is the P type, this is the N type. These are connected to a resistor. Current I is flowing. So it will be receiving electrical energy and it will be generating current. So current will be, electricity will move on. This is how it works. And see, graph is also a bit different. If this is for voltage, this x-axis represents voltage, and this y-axis represents the current. So see, the graph of it is in this manner. Now you have to understand one thing. When the voltage is over here, this means what is the value of current when we have some V voltage?
0.
0.
0. So when current is 0, what kind of circuit is it? We have done it today.
Short circuit.
Current is 0. No current is
Open
flowing.
circuit.
Open circuit.
Yes, Abdullah is getting confused again. Abdullah, whenever we have no current, the circuit behaves as an open circuit. Fine. And see, regarding here, the current has some value. What about the voltage?
0.
Voltage will be 0. So voltage will be 0 and it will be having some current, and this will be the maximum current. So this will be, because see, these are the lesser values and there is no graph beyond it, which means this is the maximum current. So here the circuit will be short circuit. This will be the short circuit, voltage will be 0. Clear? If this is point is C, let's say this point is C, so this will be IOC. Clear? All these devices are clear?
Yes, ma'am.
Just note down these. Yes, Abdullah, this is all about semiconductors. If you have to leave, you can leave if you have noted it down.
Ma'am.
Yes.
Now, what is that infrared LED?
Infrared LEDs, these are LEDs which comprise or which release infrared radiations. You must have studied those spectrum, electromagnetic spectrum. Yes.
Ma'am, I'm asking what is GAAS?
Okay, gallium arsenide. Gallium arsenide.
Okay. Class over.